Warning! Formalism is making its debut. This will be a mathematically intensive chapter and will bring in a whole host of new notation. Comment or message on IG if you need help or even more supporting resource. Now, early on, we saw that for a physically realizable system or solution, there was a need for a certain type of function, namely a normalizable function, where psi x of t was, in the magnitude squared, or psi star psi, equal to 1. This is what represented the physically realizable situation. Here, we make explicit reference to a specific vector space known as Hilbert space, which is actually kind of short in scope for what a Hilbert space is, because it's actually a complete inner product space. Let's take a look at what this means. Here we see that we have a hierarchy of spaces, and in mathematics, space is not like the x, y, z that we see here in the physical world. Space means a collection of items, namely vectors or functions, that we wish to analyze certain properties on. Topological, as you see, encompasses more. Metric spaces, we're looking at things like distances. Then the normed vector spaces, we need to be normalized, so it makes sense that the inner products live in normed vector spaces. But nonetheless, this is the hierarchy, or a type of a way to illustrate that these function and vector spaces branch out to several other categories, and we're making explicit reference to the Hilbert space. What you really need to know about this is that we're just trying to use the small reference or small subset of spaces that are what are called L2 or square integrable functions. And this is just telling you that we need a square integrable function that is normalized. I'm just repeating myself at this point. But, again, these hierarchies are coming, different sizes. And here's a couple more reference points here over in the left if you wish to see how they kind of extend out and get more hyper specific. But that's a rabbit hole for another day. What I'd like to point out, though, is that there's a lot more to this picture and a lot deeper of understanding that we can gain if we simply understand the scope of what we're restricting these functions to. So without further ado, let's dive into this particular question. For part A, we want to know what range of nu is the function f of x equals x to the nu power in Hilbert space. So what we need to find is what nu allows this to exist in Hilbert space on a specific interval 0 to 1. Assume nu is real, but it's not necessarily positive. B. For the specific case of nu equals 1/2, is f of x in this Hilbert space? What about x times f of x for nu equal 1/2? And what about the derivative of f of x for nu equal 1/2? So we got a couple examples. Let's go ahead and dive on in. Alrighty, so with that, mini lesson on the annoying math out the way, let's see what it all actually means. In the Hilbert space, we primarily use the inner product definition, which is the angle brackets here of f and f, where the one on the left is denoted with the conjugate, kind of like what we saw with psi star psi. This is just a functional extension of the dot product that we saw for vectors. And again, in the L2 or the Hilbert space, what we need to have is this integral go to something finite. And that's what we will be testing against. So let's see. Here we know that our function f is just equal to x to the nu. And then again, we have to be aware that we are taking the conjugate of that. And again, as we go between functions and vectors and all that kind of stuff, realize that that notation might become sloppy, because in the matrices we have to take, or vectors, we have to take the transpose conjugate. So be aware, dimensionalities will start to seep in here. Here that we're just in one dimension or one variable, we don't have to worry about it, but be aware of what's coming. So here, since we're real for everything, but not necessarily positive, we can plug in our bounds and execute the integral, noting that we want it from 0 to 1 in the question. And it's just normal calculus, we're We're told we're real, so we don't have to worry about anything. Take the product rule or power rule, and then let's evaluate it. Plug it in 1, plug it in 0. You see that we only have one real sticking point here. 1, regardless of what power you have, is equal to 1. 0, that's what we're going to have to dive into and do a little case-by-case analysis. So let's see what that looks like. So naturally, zeros need to be handled with care. That's nothing new. We saw that in ample times throughout calculus, especially with limits. Now, if the argument is negative, which is to say that 2 nu plus 1 is less than 0, then we would get a situation where we had 1 over 0, which we know goes towards or tends to infinity, right? That blows up, so to speak. And that is not finite. We cannot have that as a condition in the Hilbert space. So not finite, not in the Hilbert space. So we know that that set of numbers is out, and now we can look at the next condition, which is to say if the argument is positive, or 2 nu plus 1 is greater than 0, we evaluate all variables to 0, right? So regardless of what nu is, so long as the argument's positive, 0 to 1 or whatever other argument is just 0 times itself, so it's 0. And we know if that's the case, then we end up at a finite number. Perfect. We like that. And so, we're good to go for the case if we solve this through this inequality. We see that nu is strictly greater than negative 1/2. So we're still left with one case, and I'm sure you could see the writing on the walls. Let's go check it out. So summarized, we have the green condition, the red condition for, the strict inequalities. Clearly, this begs the question, what about the case of nu equal to negative 1/2? Well, if we tried plugging this into the evaluation brackets, we would lead to a 0 over 0 situation, which is indeterminate. But we knew that based on the procedures and tactics we learned from the calculus classes, and that in this case we have a limitation of the power rule for integration. So now we need to go back to the integral, and we see that the inner product again evaluates to 2 times negative 1/2 instead of 2 nu. And you see here that we get x to the negative 1. Power rule here doesn't work. We know we need to use a natural log. Not only that, but the 0 over 0 that we had in the brackets of evaluation, we also had to divide by 0. Again, not going to work. So nonetheless, we're back to the integral, and now you see we have to examine what happens for ln evaluated at 1 and 0. Not too much more work. We see here that plugging it in, ln of 1, 0, ln of 0 goes to infinity. Uh-oh, we don't like infinity. Infinity is not finite, not in the Hilbert space. So we know that f of x is in the Hilbert space only for the case of the strict inequality of greater than, which is boxed here. So this is how you go through these definitions and check in kind of a general sense what the context is saying. Those hierarchy graphs that were showed earlier, that just shows you how things get generalized for other cases. And you can see how mathematicians play these brain games of having fun for, well, these type of functions, that type of function, yada, yada, yada. Here, we're able to boil it down to a specific narrow scope of function, and that's what quantum mechanics will use for the rest of the theory. Now, for B, if we let nu equal 1/2, remember our nu bound was negative 1/2, so if nu is equal to 1/2, then we see that this is also greater than the negative 1/2 condition, so f of x would be in the Hilbert space. So we're good to go there. As you see, setting up conditions makes it a little easier, and that's what we can use to compare. Nonetheless, the next question, or the next part of B that we were asked about, was what happens if I multiply this f of x by x? Here we just have a simple procedure with exponents, combine the exponents. We see here that that leads to 3/2, which is, greater than the negative 1/2. So yes, we're good there. All right, so to recap the last position that we had, this x times f of x, we could say that yes, the f of x times f of x is in the Hilbert space for the case of nu equal positive 1/2. Now what happens if we take the derivative of this function for nu equal 1/2? Put the 1/2 in as you see here, take the derivative. Now you see that nu actually gets morphed to, via the operation, the derivative operation. Derivatives are operators, so it transforms the function. And we see that we have a negative 1/2 in the power now. And here nu is equal to negative 1/2, which is not greater than the negative 1/2 condition. So what we could say here is that d by dx of f of x is not in the Hilbert space. That's weird. You could see here that a similar operation of multiplying by 1 over x would yield the same thing. So the authors wanted to make a note of this, that the moral here is simple operations such as differentiating or multiplying by inverse powers, in this particular case, can carry a function out of Hilbert space. So knowing that we have to talk about operators in a large part of the rest of the theory, understand that these operators have to be closed or complete, meaning that if you operate on it, you get something else that is also in the space. More on that here soon, but that's your nice little introduction to Hilbert space and what we need it for. So we'll let you go to the next one. Thank you for dealing with my ranting and watching. As always, until next time, happy learning.